I want you to close your eyes for a second.
Yeah.
Imagine you're sitting in your car on this brand new, massive superhighway.
Okay.
It is a marvel of engineering. The asphalt is jet black. Lines are crisp white, 4 broad lanes stretching all the way to the horizon. You can practically smell the fresh pavement.
Sounds like a dream commute.
It should be.
Mm.
But, and here is the absolute kicker, the Highway Authority has come along and put up these huge concrete barriers blocking 3 of those 4 lanes.
Oh, that is painful.
It's agonizing.
Yeah.
You look out your window and you see miles of unused asphalt just sitting right there, perfectly pristine, while every single car is forced to merge into one single cramped lane.
Inefficient.
It's so inefficient, it feels like a total waste. And honestly, it just creates a massive bottleneck.
And in our world, the networking world, that bottleneck is latency and eventually packet loss.
Exactly. But here's the thing. This isn't just a traffic report. This is exactly what happens in switched networks if you're just relying on the default settings. It's a phenomenon called single-link congestion. And our mission for this deep dive is to figure out how to move those concrete barriers.
We're going to fix the traffic jam. We're looking at a stack of documents today covering Etherchannel, or the technical term is link aggregation.
The goal seems simple enough. We want to figure out how to take that single congested lane and turn it into the multi-lane superhighway it was designed to be.
Right.
And the best part, according to these notes, we don't need to buy any expensive new hardware to do it. We just need to be smarter than the default configuration.
That's it. It's really about solving what network engineers often call the paradox of redundancy.
I love a good paradox. Let's start right there. Why do we even have this problem? Why would a network architect build a 4-lane highway, or in our case, run 4 physical cables between switches, only to have the system just voluntarily use one?
It comes down to fear or, if we want to be generous, risk management. Network architects are obsessed with redundancy. They are terrified of a single point of failure. So if switch A connects to switch B, they rarely run just one cable. They'll run 2, 4, maybe even 8 links between them.
Which makes sense. If a rat chews through a cable or someone trips over a wire, you don't want the whole company going offline. You need backups.
Precisely. The goal is backup. But there is a major obstacle standing in the way of using all those cables at once. It's a protocol we've touched on in previous deep dives, STP, or spanning tree protocol.
Ah, yes. Safety net.
The safety net, or as some frustrated engineers call it, the fun police. STP is enabled by default on pretty much all layer 2 switches. Its one job, its only job, is to prevent catastrophic switching loops.
We hear loop and we think roller coaster, which is fun, but remind us why a network loop is basically the apocalypse.
It's bad. I mean, really bad. In a switched network, if you have multiple paths for data to travel in a circle, broadcast frames, those are messages for everyone, they can spin around that circle forever. And they don't just spin, they multiply. Within seconds, you have a broadcast storm. It just eats up all the bandwidth, the LEDs on the switches go solid green, and the CPUs just crash. The network effectively melts down.
So to stop the network from melting down, spanning tree acts like that paranoid highway authority.
Exactly. To ensure there is only one active logical path and absolutely no loops, spanning tree looks at those 4 cables you plugged in, picks the best one to use, and ruthlessly blocks the other 3.
It blocks them.
Puts them in a blocking state. They're physically plugged in, link lights are on, electricity is flowing, but the switch just ignores any data trying to cross them.
And that is the paradox.
Yeah.
You spend the budget on extra cabling, maybe expensive fiber optics, all for better performance. And the safety protocols force, 75% of your investment to just sit idle? The notes here say 50% or more sits idle, wasted. That's hard to swallow.
It's incredibly inefficient. You might have 4 1-gigabit connections physically connected, but because of STP, you are effectively limited to just 1 gigabit of throughput.
Okay, so we have the problem. The highway is blocked. Enter the hero of our story, logical aggregation. How does Etherchannel get around the fun police without causing a meltdown?
The solution is actually a bit of a magic trick, or maybe a disguise. Etherchannel groups multiple physical Ethernet links into a single logical link.
When you say logical, you mean it's a simulation, like a virtual interface.
In a way, yeah. Think of it like 3 kids in a trench coat trying to sneak into a movie. You take those 4 physical cables and you bundle them together in the configuration.
Okay.
You tell the switch, hey, don't look at these as 4 separate interfaces. Treat this whole bundle as one single interface. which we call a port channel.
I see. So the switch puts the trench coat on the cables.
Mm-hmm.
And because the switch presents it as one big pipe instead of 4 little pipes.
Spanning tree sees only a single path.
Ah.
Since there's only one logical path, there are no loops. Since there are no loops, spanning tree doesn't block anything.
That is clever. So the concrete barriers just come down.
All of them, all the physical links become active at the same time. You get full bandwidth utilization, but you still keep the safety of loop prevention because, logically, it's just one line.
So we're basically tricking the safety protocol into letting us dry fast.
Yeah.
Okay. Now, aside from just going faster, let's look at the value proposition. The research highlights 4 key benefits. The first one is, obviously, bandwidth.
Right. You're aggregating the speeds. If you have 4 1 gigabit links bundled, you've created a 4 gigabit logical link. This is huge for cost savings because you didn't have to go out and buy an expensive 10 gigabit fiber card or upgrade your chassis.
Right.
You just use the copper ports you already had.
That's the free upgrade part.
Mm-hmm.
But the second benefit listed here is load sharing. And I want to pause here because I feel like this is where people get confused.
Mm-hmm.
If I have a 4 gigabit Etherchannel, does that mean I can download a single file at 4 gigabits per second?
I am so glad you asked that, because it is the #1 misconception about Etherchannel. The answer is no, you cannot.
Wait, really? But we just said it's a 4 gigabit pipe.
It is, in aggregate. But think back to the highway. Even if you open 4 lanes, a single car can still only drive in 1 lane at a time. It can't drive in all 4 lanes simultaneously.
That would be a very wide car.
Exactly. In networking, a car is a conversation, a flow. Etherchannel uses a hashing algorithm to balance the traffic.
Okay.
The switch looks at the traffic headers, specifically things like the source and destination IP address, or MC address. It runs a math equation on those addresses to assign that specific conversation to one of the links in the bundle.
So if I'm transferring a huge video file to a server,
That specific conversation has one source IP and one destination IP. The math says you go to lane 1. That transfer will max out at the speed of that single link 1 gigabit. It won't exceed it.
but if my colleague in the next cubicle is also transferring a file to a different server,
The math equation for their IP addresses will likely yield a different result, putting them in lane 2, so you're not slowing each other down.
got it. So it's not that one car goes 400 miles per hour. It's that the highway can handle 4 cars side by side at 100 miles per hour.
That's it, exactly. It creates width, not raw single stream speed. It optimizes the aggregate flow of all users. If you have 100 users, they get spread out across the lanes so everyone feels like they have more speed.
That is a crucial distinction. Okay, now what about the redundancy part? Since we're now using all the links, do we lose our backup plan?
Not at all. In fact, the failover is much, much smoother. If a rat does chew through one of those 4 cables, the ether channel doesn't go down.
Okay.
The topology doesn't change. The switch just instantly recalculates that hashing algorithm and moves the traffic from the broken link to the remaining 3.
And the big win there is that spanning tree doesn't have to get involved.
Correct. Usually without either channel, if a link goes down, STP has to wake up, freeze traffic, listen for BPDUs, and do some math to unblock a backup port. That can take anywhere from a few seconds to nearly a minute, depending on your config.
What?
With Ether channel, STP sleeps through the whole thing because the logical link never went down. It just got slightly slower.
That's reliability.
Right.
And the 4th benefit listed is consistency.
This is a quality of life feature for the engineers. Once you create the bundle, you apply your settings like VLANs or trunking modes to the port channel interface. The switch automatically pushes those settings down to all the bundled physical ports.
So you don't have to configure 4 ports individually and, risk making a typo on port 3.
Exactly. It forces synchronization.
Okay, we're sold. We want the bundle. But apparently, we can't just plug cables in and hope for the best. The switches need to agree to do this. They need to speak a common language.
They do. You can set them up statically, which is just forcing them to be on, or you can let them negotiate dynamically using a protocol.
And we have 2 main contenders here. It feels a bit like the old VHS versus beta war, or maybe iOS versus Android. We have PAgP and LACP. Let's look at PAgP first.
PAgP stands for Port Aggregation Protocol. The most important thing to write down about PAgP is that it is Cisco proprietary.
So, members only.
Strictly members only. It was designed for Cisco to Cisco connections. If you're connecting a Cisco switch to a Juniper firewall or a Dell server, PAgP simply won't work.
Right.
The other device won't understand the packets. It sends special packets every 30 seconds to check for consistency, but it's a walled garden.
Okay, and in the other corner, we have LACP.
Link Aggregation Control Protocol. This is the industry standard. It's IEEE 802.3 AD, or more recently, 802.1AX.
So this is the universal translator.
Yes. If you are in a multi-vendor environment, which, let's be honest, almost everyone is these days, you use LACP. It works on Cisco, it works on HP, Linux servers, VMware hosts, you name it.
Does it have any features that PAgP lacks besides just being open?
It does. It has a feature called Hot Standby. LACP allows you to define up to 16 links in a bundle, but typically hardware only supports 8 active links.
Okay.
LACP lets you keep the other 8 in standby mode, like a substitute teacher sitting in the classroom.
I like that.
If one of the active links fails, the standby link is already negotiated and ready to jump in instantly. PGP doesn't really do that.
So, generally speaking, unless you're running a museum of vintage Cisco gear, LACP is the way to go.
That is the consensus.
Yeah.
LACP offers the most flexibility.
Now, this leads us to the negotiation game. The source material breaks down the modes of operation for these, and honestly, the analogy that jumps out at me is modern dating.
It really is. It's all about who is brave enough to make the first move and who's just waiting by the phone.
Let's look at PGP first. We have 3 modes: on, desirable, and auto.
Right. So mode on isn't really a negotiation. It's the brute force method. You're telling the switch, I don't care what the other side says, you are an Etherchannel. It sends no hello packets.
That sounds risky.
It is. If the other side isn't set up exactly the same way, you create those loops we talked about. Very dangerous.
Okay, so that's forcing the relationship. Not healthy. What about desirable?
Desirable is the extrovert. The interface actively initiates negotiations. It sends out PAgP packets saying, hey, I want to form a channel, do you?
And auto?
Auto is the introvert. It's passive. It just waits to receive a packet before it responds. It will never, ever start the conversation.
So here's the scenario. If I connect a switch set to auto to another switch set to auto,
nothing happens. The silent treatment?
nothing.
Both sides are listening. Neither side is talking. You get no ether channel. They just function as individual links. And STP likely blocks all but one. It's tragic.
So for PHP to work, at least one side must be set to desirable.
That's the rule.
All right, let's flip to LACP. The terminology changes, but is the dynamic the same?
Very similar. We still have on, which works the same dangerous way. But for the negotiation, instead of desirable, LACP uses the term active.
So active is the initiator.
Yes. The port initiates negotiations by sending LACP packets. And instead of auto, LACP uses passive. The passive port listens and responds, but it won't start the chat.
So the golden rule is the same then?
Yes. You cannot have passive plus passive. One side has to be active for the link to form. And, crucially, you can't mix protocols.
Right.
You can't have one side set to desirable speaking PAgP and the other side set to active speaking LACP. One is shouting in French, the other in German. Nothing happens.
Okay, let's get our hands dirty. We want to implement this. But before we start typing, there's a pre-flight checklist. The material emphasizes that the member ports, the physical cables, must align perfectly.
This is critical. It's not a suggestion, it's a requirement. If you ignore this, the switch will suspend the ports to protect itself.
Walk us through the list. What needs to match?
First, interface types. You can't mix media, can't group a fast Ethernet port with a gigabit Ethernet port.
Okay.
Second, speed and duplex. They have to be identical, can't have one side set to half duplex and the other to full.
And then we get into the VLAN stuff, which is where I imagine most people mess up.
Oh, absolutely. VLAN consistency is huge. All ports in the bundle must be in the same VLAN if they're access ports, or if they're trunks, they must have the same native VLAN.
And the VLAN range too, right?
Correct. If port 1 allows VLANs 1 through 100 and port 2 only allows 1 through 50, they cannot form a bundle. The parameters must be identical.
What happens if I try it anyway?
The switch is smart. It'll put the ports into a suspended state or even disable. Basically, it shuts them down to prevent problems.
Okay, checklist complete. We have compatible ports. Now we're at the command line. Walk us through the workflow.
It's a 3-step process. Step 1. Select interfaces. Use the interface range command to grab all the physical ports. For example, interface range fasten at 012.
Got it. Step 2.
Create the bundle. This is where the magic happens. The command is channel group IDE mode.
And that mode part is where we choose our language.
Exactly. If you type mode active, you're choosing LACP. If you type mode desirable, you're choosing PAgP. You hit enter and the switch creates a new virtual interface.
Which leads to step 3, and this brings us back to that consistency benefit.
Yes. Step 3 is configure the logical interface. You enter interface port channel ID. Now, any configuration you apply there, like switch port mode trunk, applies to the whole bundle.
There's a big warning box in the material here. It says, do not configure trunking or VLANs on individual physical ports after the channel is formed. Why is that?
Please don't do that. That is how you break the bundle. If you go back and change the VLAN on just physical port 1, it creates a mismatch with port 2. The switch will detect that and kick the port out of the bundle.
So rule of thumb, once the bundle is born, you only talk to the parent, the port channel, not the children.
That's a great way to put it, yes. Talk to the port channel.
Now we've typed the commands. How do we know it actually worked? Trust but verify.
The go-to command is show Etherchannel summary. It gives you a nice one-line status.
And we're looking for specific flags here. It's like reading tea leaves, but with letters.
We want to see SU. The S stands for layer 2, and the U stands for in use. If you see SU next to your port channel, you are golden.
And what are the bad flags? What tells us we broke it?
D is bad, D means down. But a tricky one is I, or sometimes P. If you see it labeled as standalone, it means the port is physically up, but the negotiation failed. It's not part of the bundle.
If we see those bad flags, what are the usual suspects?
It's almost always a mismatch. VLAN mismatch is number 1. Or trunking mode incompatibility. One side is trunk, the other is access.
Or maybe you tried to mix LACP and PAgP?
Yes, the protocol mismatch. Or, going back to our dating analogy, you left both sides as auto or passive. They're both just sitting there waiting for a call that never comes.
Before we wrap up, there's a tip box here that I think is important because the acronyms are so similar. It distinguishes between Etherchannel and DTP.
Yes, very easy to confuse.
Yes.
Etherchannel is what we're talking about today, aggregating links. DTP, dynamic trunking protocol, is totally different. DTP just automates the creation of a trunk link versus an access link.
So DTP decides, are we a road or a parking lot?
No.
And LACP decides how many lanes is the road.
That works. That's a good way to look at it. They have different jobs.
Excellent. Okay, we have covered a lot of ground. We've gone from traffic jams to superhighways. Let's bring it all home. What are the big takeaways?
The goal is clear. Stop wasting bandwidth. Use Etherchannel to bypass STT blocking and use the hardware you already paid for.
And when it comes to the how, what's the recommendation?
Stick with the standard. Use LACP and set the mode to active on at least one side, preferably both, just to be safe. It gives you the most flexibility.
And for maintenance.
Discipline. Apply all your configuration changes to the port channel interface. Treat the logical bundle as the real interface, and let the switch handle the physical details.
It really is a fascinating concept when you step back.
Yeah.
We're essentially creating a logical fiction, this fake port channel interface, just to convince the rigid physical reality of spanning tree to let us do what we want.
It is. We're using virtualization to bypass safety protocols safely. It's basically a hack that became a standard.
It makes me wonder, where else in technology, or even in life, do we use a logical layer to smooth over the messy limitations of the physical world? We trick the system to make the system work better. Something to think about next time you're stuck in traffic, wishing you could open up those extra lanes. Thanks for diving in with us.
A pleasure, as always.